Resit paper question number 4. In this paper you're using this power series, which is a way to rewrite the sign of x as a whole series of terms involving x, x cubed, x to the 5 and so on. And the more terms we add, the nearer we get to the value of sine x, you may remember. But we can use this power series as a way to write down and help us to integrate something like this, which is not straightforward to integrate. We can do it. In fact, in part C, you're asked to try and do it using integration by parts. And so we'll have a go at that at the end. But the first step is to try doing it this way. So part A, use this series to write down the first 5 terms of the power series for x sine x. Here it is. There's the power series for sine x. So if you think about it, that's straightforward. If the power series for sine x is this, minus x to the 7 over 7 factorial, and you can see the pattern, I hope, plus x to the 9 over 9 factorial minus da 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 da. That's the power series for sine x, and so I've got to do is multiply that by x, because I want x times sine x. So if you think about it, that's going to give me, if I expand out the brackets, x times x is x squared, minus x times x cubed is x to the 4 over 3 factorial. And then the next two, x times x to the 5 will give me x to the 6. X times x to the 7 will give me x to the 8. In other words, I just rewrite this series, add 1 to the power. And so on. So if this in fact had not been x, but had been x squared or x cubed, I would just do a similar sort of thing. So now, if I want to integrate this function, I can just integrate each term in order. And that's what you're actually asked to do in part B. Use the power series you wrote down in part A to evaluate this integral here. So what I do is, instead of integrating this, I integrate the power series that I've just written down, this. And the question asks you to do just the first 5 terms, so 1, 2, 3, 4, 5 terms. So I write down the integral and integrate it. So have a go. So what I'm going to do is say that the integral of x sine x is approximately given by, remember the more terms we add, the better our approximation becomes. It's approximately given by the integral of each of these terms. So I'm effectively integrating each part in turn, and then I'm going to put the limits in 0 to 0.4 and work out the answer. And for each one, I just add 1 to the power and divide by the new power. Add 1 to the power and divide by the new power. Add 1 to the power and divide by the new power, and so on. Remember that 7 factorial, for example, means 7 times 6 times 5 times 4 times 3, but you have got a button on your calculator which tells you the factorial. And if you've got the calculator, same sort of calculator that I've got, it's this button here, the shift button. If you look above the x to the minus 1 button at the top here, so shift and then this button, we get x factorial. So you have a go, and then pause and have a go, and then we can restart the video and I'll show you the solution. Okay, if we have a look at it then, done your integral, I've added 1 to the power divided by the new power, added 1 to the power divided by the new power, and so on. And then I've worked out what each of these denominators is here. And then I've put the limits in 0.4 and 0. Well, luckily for us, for 0, if x is 0, then all of these terms disappear. So the second one is just 0. So all I've got to do is put x equals to 0.4 in each of these. So 0.4 cubed, 0.4 to the power 5, and so on. Put those values in. I've done it in one hit on the calculator using the fraction button and the power button for these. And I end up with that answer to 3 significant figures. Now part C asks you to use integration by parts to evaluate direct this definite between. So let's have a go at it. Okay, so here is the formula for integration by parts. Integral of u dv equals uv minus integral of v du. So we've got to call one part of this u and one part of this dv. And then the bit we call u we differentiate to get du. The bit we call v we integrate to get v. So the key is to think about the bit we call u, because if I differentiate that and x disappears, I'm left with an integral I can do. And if you look at this, if I let u equal x, then the difference with x is just 1, so x will disappear and we'll be able to do it. So that's what I do. I let u equal x and I let dv equal sine x. So now using my table of differentials and integrals, I have to differentiate u and I have to integrate sine x to get v. So the u by the x is just 1 because the differential of x is 1, and the integral of sine x from the table of integrals is minus cos x. We don't worry about the c at this stage, we just put that in right at the very end if we need to, but actually in this particular case, because we're doing a definite integral, we don't bother with c at all. So I can now say, putting these in, that my original integral 4 of x times sine x equals uv, so u is x, v is minus cos x, minus the integral of v, which is minus cos x, du, which is just 1. And so now x has disappeared and I'm left with an integral I can do. Remember, that's all got to be between the limits of 0 and 0.4. So now it equals minus cos x times x gives me minus x cos x, minus minus gives me a plus, the integral of cos x dx between 0 and 0.4. Now the integral of cos x is sine x, so that's going to give me minus x cos x plus sine x between 0 and 0.4. So now I just put my values in, and remember that if I'm talking about values like this, then I must be letting x equal 0.4. I can't be in degrees, I must be in radians. So check you're in radians before you put these values in. You might be able to make life a bit easier for yourself, because can you think about what the sine of 0, when I put x equals 0, and what's the sine of 0 and what's the cosine of 0. That might help you speed up your work. So have a go. Again, I'll do the solution and you can have a look at it below. So putting in the limits, minus 0.4 cos 0.4 when x is 0.4 times the sine of 0.4 minus, well, if x equals 0, then this whole first term is gone, because 0 times anything is anything, plus the sine of 0. And you might remember that the sine of 0 is 0 anyway, and so we end up with just the top limit, which is this. So putting those values in, we get 0.021, which is exactly the same answer as we had before. So that's question number 4 done.